Okay, so we have been looking at contact angle, and we saw that if you know the surface tension between liquid gas, solid liquid and solid gas interfaces, then we will be able to calculate surface tension, right. So now we will go ahead and talk about, in case of capillary flows, when the gravity is becoming important, okay, when the gravitational force need to be accounted for. So if you consider a fluid volume of omega and having a the liquid air interface of d omega, then we try to see in what situations we need to consider for the gravitational force. So we need to minimize the equilibrium position of a gas liquid interface can be determined when the Gibbs free energy is minimum, okay. And for the Gibbs free energy to be minimum, the summation of the surface energy and the gravitational potential energy need to be minimum, okay. So let us look at the capillary length and capillary rise, and here we consider liquid volume omega with free liquid air interface d omega. Now if you want to determine the equilibrium shape, then the free energy needs to be minimized, okay, and this free energy has the surface energy plus the gravitational potential energy, okay. So we can write this, the G minimum will be, you have to minimize the surface energy gamma into d omega into A. So this is the capillary radius, this is surface tension, and this is integrated over the interface plus rho into G integration dr integrated over the volume into Z, okay. So this gives you the volume of the fluidic element, and this gives you the interface length. So the entire term is minimized for a fixed volume omega, okay. So if you talk about a liquid drop present in a free space, the liquid drop volume will be spherical, okay. To minimize energy, the volume has to be spherical, because in this case the gravitational potential energy is 0. So we are basically minimizing the surface area for a fixed volume. So the minimum surface area for a fixed volume is a sphere, okay. So that is why in free space the liquid drop takes a spherical shape, and when we have gravity present, to account for the gravitational forces, we would define a parameter called capillary length, okay. So we would define a parameter called characteristic length, okay. We can also call it as capillary length, so L capillary. So characteristic length for capillary flow is gamma over rho G, okay. So it is basically the competition between the surface energy and the gravitational potential energy, right. And so if A, okay, so as you see here, A is less than gamma over rho g, okay, if this condition is satisfied, then we say that gravity can be neglected, gravity can be neglected, okay. So the radius of the capillary, if it is less than the characteristic capillary length, then we can say that gravity is neglected, right. Now we can find for water air interface at 20 degree centigrade, you can find L cap, the characteristic capillary length would be gamma will be 0.073, density will be 1000 into 9.81 is Z. So it is about 2.7 millimeter, okay. Now in case of capillary flows in microchannels, the radius of the microchannel or the capillary is less than this value, less than 2 millimeter, 2.7 millimeter. So we can say that for all capillary flows in microchannels, the gravity force can be neglected, right. So in practical microscale capillary flows, the radius of the capillary A is less than L cap. So the rho z is less than gamma over S square, right. So gravity does not influence, okay. So capillary flows at microscale are not affected by gravitational force, okay. So having talked about that, let us talk about capillary rise. We know that when you put a small capillary into a liquid container, the liquid tries to move off the capillary, okay. Here we try to find out what would be the maximum achievable height up to which the liquid will rise, okay. So let us look at, let's move on to here. So this is the illustrative figure. So we look at capillary rise height. So this is the situation as you see here, okay. For simplicity we are considering a vertical tube into a liquid present here, and we are satisfying the condition that the radius of the capillary is less than the characteristic capillary length, and the gravity is in the vertical direction, okay. So G is along the vertical direction, along the z direction, and theta is the contact angle as you see here. So this angle is going to be theta, this angle is going to be theta, which we call contact angle. Contact angle is theta, right. So this is theta, and the surface tension liquid air interface, liquid air surface tension equal to gamma. So, here we assume that the radius of the capillary is less compared to the characteristic length scale, which mean that gravitational force is negligible, and if gravitational force is neglected, we can expect the interface to be spherical in shape. Okay. So, that is the reason why the interface in this case will be spherical in shape. So, this is what is shown here. So, this is a spherical interface, okay, spherical interface. So, if you look at the geometry, this is the radius of this sphere, okay, and this is A is the capillary radius, R is the radius of this interface, okay. So, if you use geometry, then this contact angle, this angle will be same as the contact angle, which is theta, okay. So, by geometry we can look at cos theta, here you can write cos theta will be equal to A over R, right. So, R will be A over cos theta, right. Now, in this particular case, for a curved interface we would have two different radii of curvature, okay. Since here in this case the radius of curvature is spherical, the two radii of curvature are equal, okay. So, we can say that the two radii of curvature are equal. So, we can say R1 equal to R2 will be equal to A over cos theta, okay. So, now we try to do a force balance, okay. So, here if you look at the interface, okay, if you look at the interface, the if the interface is convex in shape, so the pressure would be higher in the convex side as compared to the concave side, okay. So, in this particular case, since at the convex side we would have air present and at the concave side we would have liquid present, okay, as you can see here, at the concave side we have air present here and liquid is present there. So, the pressure on the air side is more as compared to the liquid side, okay. So, we can write here the pressure difference is pressure higher in convex or air side compared to concave or liquid side of the interface. So, if pressure on the liquid side of the interface we call it as P liquid at height h, okay. So, we can say P liquid at height h will be equal to P0 is the atmospheric pressure minus the Young Laplace pressure delta P surface, okay. So, this is the Young Laplace pressure across curved interface. Whenever the interface is curved we would have Young Laplace pressure present. So, we can write P0 minus 2 gamma over A into cos theta, okay, because we know that delta p across the surface is 1 over r1 plus 1 over r2 into gamma. This is what we derived earlier. So, this here r1 equal to r2 and they are equal to a over cos theta. So, you can write 2 gamma over a into cos theta, okay. So, let us call this equation 1. Now, at this location here, okay. So, this is a point which is in the liquid air interface, but far away from the capillary. So, here the pressure will be P0 same as the ambient pressure, because this interface is flat, and as we know the Young Laplace pressure drop across a flat interface is going to be 0. So, the liquid pressure will be same as the ambient pressure P0, okay. So, here we know that P liquid at 0 at z equal to 0 is the pressure away from tube, and that will be equal to P0, okay, and this is because Young Laplace pressure drop across flat interface will be 0, right. So, this is P0, we can write this P0, okay. So, this pressure here is also going to be P0 because they are at the same level, okay. So, you can write P0 is going to be P liquid at h plus rho g h, okay. So, you can write P0 will be equal to P liquid at h. So, this is the pressure at the liquid side of the interface plus the hydrostatic pressure rho g h, okay. So, let us call this equation 2. Now, if you combine equation 1 and 2, if you substitute P0 from here in there and rearrange the term, what you get is this. So, using 1 and 2, what you get is h equal to 2 gamma divided by rho z a into cos theta, okay. And this you can write it as, you can write 2 L capillary square, okay, gamma over rho g square root is L cap. So, L cap square divided by a into cos theta. You can also write this as 2 over rho z a into gamma solid gas minus gamma solid liquid. Remember, this gamma is gamma between liquid and gas, okay. And we know that cos theta equal to gamma solid gas minus gamma solid liquid minus divided by gamma liquid gas. So, you can substitute for gamma liquid gas, gamma liquid into cos theta is gamma solid gas minus gamma solid liquid. So, now if you take an example, so you consider one example, let us consider a PMMA channel and let us say 100 micron radius. We can find that the capillary height is going to be 4.2 centimeter, okay. And if you consider water as the liquid. So we know the density H is going to be 4.2 centimeter. Now if you instead of 100 micron radius, okay, if you go for the same material and liquid water and the radius is 10 micron, then H will be 10 times, okay, H will be 42 centimeter, okay. Now if you look at this equation, you know this equation here, H equal to 2 gamma divided by rho Ga cos theta, H equal to 2 gamma over rho Ga cos theta. Here it is possible to measure contact angle, the capillary height, this will be known for a liquid and this will be known for a capillary. So it is possible to find out gamma. So gamma can be calculated, okay. So it is possible to do an experiment, okay, where we would know you know the capillary radius, we can measure the contact angle, we can measure the capillary height to predict what the surface tension would be for a liquid, okay. So next we move on to talk about the capillary rise time. We talk about okay. So we know that if you put a capillary or a microchannel, we can expose it to some liquid, because of the capillary action the liquid will move into, okay. And we found an expression for, in case of a vertical capillary, what is going to be the maximum height to which liquid will move. Let us look at what is the time scale up to which this maximum capillary height can be attained, okay, and how it is going to achieve this maximum height, okay. So for that you know we would consider the equilibrium height. So the equilibrium height H, and so that we would find the rise time required, okay. Let us say LT is the height of liquid column at time t, okay, and this equilibrium can be attained. So equilibrium L infinity will be equal to H. So as time would tend to infinity, the liquid would reach the equilibrium height. First let us do mass conservation, okay. If you do mass conservation, we can write dl over dt, okay, the change in the height, or this is the speed of rise, will be equal to the velocity, right, u0, which will be equal to the flow rate divided by pi a square. A is the capillary radius, and we can substitute for q from Hagen-Poiseuille, where q can be written as pi a4 divided by 8 eta L into delta p. So we can write this as a square delta p, which is a function of time, into 8 eta into 1 over LT, okay. So all are time dependent here, right. Now we can do energy balance. So, when we put a capillary in a liquid, the liquid tries to pull up, and this is because of the Young Laplace pressure that is present across the interface, and this pressure is utilized to overcome the viscous drop and also to overcome the potential energy because of any gravitation present, okay, however small that might be. So, you can write the energy balance. We can write the Young Laplace pressure drop will be equal to the viscous pressure drop plus the hydrostatic pressure, the potential energy of liquid column. Okay. So, we can write delta P surface will be equal to delta P at, so this is the viscous plus rho into G into LT. So, this is the hydrostatic pressure and this is the viscous pressure drop, right. Let us call this equation 2 and let us call this equation 1. Let us call this equation 1. Okay. Now, if you insert this equation 2 expression for the Young Laplace pressure here, okay, sorry, not Young Laplace pressure but the viscous pressure drop, okay, which can be substituted here, If you do that, what we get is this, we get d L T over dt will be equal to a square over 8 eta LT, okay, a square over 8 eta into 1 over LT into delta PT, which will be equal to delta P surface minus, which is the Young Laplace pressure, minus rho G into LT. And we have an expression for this, right, which will be 2 gamma cos theta over A, right. So, if you substitute now, if you simplify, you get d LT over dt will be equal to gamma over 8 eta into 2a cos theta 1 over LT. So, divided by LT minus rho G a square over gamma, okay. So, which can also be written as rho G a square divided by 8 eta into h over LT minus 1. So, this is d LT over dt, right. Now, to proceed further, let us try to non-dimensionalize this equation, okay. So, we use some characteristic scales. We can say T is the characteristic capillary time scale into T star, and where tau capillary will be equal to 8 eta h over rho G a square, and we can say L will be equal to h into L star, okay. H is the maximum capillary height and L is at time t. Now with that we can write this equation in non dimensional form. So, we can write d L star t star divided of dt star. So, dlt over dl square L star t star of dt star equal to 1 divided by L star t star minus 1. So, this is the equation that we have to solve. So, with the boundary conditions, what are the boundary conditions? The boundary conditions are L star at 0 is going to be 0. So, when time t equal to 0, this is going to be 0, and when time t equal to infinity, L star infinity will be equal to 1. Okay. So, because L will be h, L star will be 1. With that we can have two extreme cases. In case 1, we say that the time t star is less than 1. Okay. So, L star is less than 1. So, we are talking about at the beginning of the capillary rise. Okay. So, in that case we can write d L star t star over dt star. L star is small compared to 1. So, 1 over L star will be very large. So, we can write, so 1 can be dropped off there. So, L star t star. So, you can write L star t star will be equal to square root of 2 t star. Okay. This is valid for t star less than 1. Now, we can consider the second case, case 2, and here the time will be large. Okay. So, t star would tend to infinity. So, which means that L star will tend to 1. Okay. So, in that case we can write L star equal to 1 minus delta into L star, delta being very small. So, you can say that where 0 less than equal to delta L star less than 1. So, we can write d L star t star over t t star will be equal to 1 divided by 1 minus delta L star minus 1, right. So, this is this equation. Okay. Instead of L star we substitute 1 minus delta L star. So, this will be equal to 1 minus delta L star to the power minus 1, right, minus 1, and this will be equal to delta L star or L star t star. Okay. So, this is the equation we need to solve. Okay. So, what we can see from here is delta L star is going to proportional to exponential minus t star. Okay, minus t star. So, you can write L star t star will be equal to 1 minus a exponential t star. So, this is the solution when t star is large. Okay. and this is the solution we obtain when T star is small. Okay. So, what we see here is, when you have capillary rise, at the beginning of the capillary rise when T star is small, it follows square root of T trend, and at large time scale it goes exponentially. Okay, it decays exponentially and achieves a steady value. Okay, asymptotically it reaches the steady value. So, this is what we see. We, let us say this is L star equal to 1, right, and this is, let us say, T star, and so this is going to vary something like this. Okay. So, this is the trend it is going to follow. What we conclude from here is initially meniscus advances as square root of T, and this is, but when time T is of the order of the characteristic time scale, then it reaches equilibrium value asymptotically. Okay. So, you take an example. If you take an example, it is the same PMMA channel case, PMMA tube, and radius is 100 micron, and we have water as the liquid, and we saw that H will be about 4.2 centimeter, and the time scale will be about 3.4 second. Okay. So, in this case you can expect that the capillary rise is going to follow the square root of T trend up to about 3.4 second, and then asymptotically it will reach 4.2 centimeter. Okay. So, now having talked about that, let us talk about few dimensionless numbers that are important in capillary flows, and the first number that we will talk about is known as bond number, which is the ratio between gravitational force to surface tension force. Okay. Dimensionless numbers. So, the first number we talk about is bond number. Bond number is the ratio of gravitational force divided by surface tension force. Surface tension force. Okay. So, we can write this. So, bond number is specified by BO, gravitational force is rho g A divided by gamma over A. So, gamma rho g A square divided by gamma will be equal to A square divided by L capillary square. Okay. So, that is how you can mathematically express the bond number in terms of the square of the capillary radius and square of the characteristic length capillary length scale. If bond number is of the order of 1, we can say that the radius of the capillary and the characteristic capillary length, they are of the same order, and if bond number is less than 1, we can say that surface tension dominates. Surface tension dominates over gravitational force, which is a case in microscale gravitational force. So, as a result our A is less than L cap. Okay. Now, the next dimensionless number that we talk about is capillary number. So, we talk about capillary number. Capillary number is defined as the ratio between viscous force to the surface tension force. So, capillary number is defined as the ratio of viscous force to surface tension force. Surface tension force. Okay. So, we can write this as eta V0 over gamma, okay, and we can write this as some velocity divided by gamma over eta. Gamma over eta is known as the intrinsic velocity, intrinsic velocity. Okay. So, this is capillary number, and if capillary number equal to 1, the imposed velocity, so this is the imposed velocity equal to the intrinsic velocity. Okay. That next number we talk about is Stokes number. Stokes number is represented by NST. So, Stokes number is given by the viscous force by the gravitational force. Which is capillary number divided by the bond number. Okay. So, Stokes number is the ratio of capillary number to bond number, which you can write as eta V0 divided by rho g s square. Okay. So, with that, let us talk about the capillary advancement in a capillary based pump. Okay. So, we talk about here capillary pump advancement times. So, we consider a flat rectangular channel. Okay. So, we consider a flat rectangular channel which looks like this, and we have this is the top channel wall. The inlet of the channel is typically larger in cross section. Okay. So, Okay. So, this is the channel wall. Here we consider this to be the interface at the inlet, which is flat. Okay, let us consider the pressure here is P0, is the atmospheric pressure. Since the interface is flat here, the pressure, let us consider this to be the interface. Okay. So, pressure here also be P0 because this is a flat interface, big interface. Let us consider this to be the Z axis, and this is X axis. This height here Z equal to H. Okay. Now, here pressure will be again P0 because this is ambient, this is the liquid, and on this side the pressure will be P0 plus delta P. Okay. This is the pressure that is pushing the liquid on this side. Okay. So, here we assume that flat rectangular channel, cross section is W into H, and we say H is less than W, right. So, we can apply Hagen partially between two flat plates used. So, if you do that, you can write Q equal to H cube W in delta P over 12 eta L. So, here it is a horizontal channel, right, it is a horizontal channel. So, the Young Laplace pressure drop will balance the viscous pressure drop because there is no gravitational force involved because it is a horizontal channel. So, these two are equal. Okay. So, you can write delta P surface is going to be 2 gamma over H into cos theta, okay, which will be equal to 2 over H gamma solid gas minus solid liquid. Okay. So, this is the expression for the Young Laplace pressure drop. Similarly, you can write down the expression for the viscous pressure drop. So, if you do mass conservation, you can write d LT over dt will be equal to V0 will be equal to Q divided by WH, right, and which will be equal to H square delta P surface divided by 12 eta. So, here you substitute for the expression for Q that we got here for a Hagen partially between two flat plates. So, this is what you will get into 1 over LT. Now, if you introduce a characteristic time scale tau advance as 6 eta over delta P surface. So, this will be 3 eta H divided by gamma cos theta, or you can write it as 3 eta H divided by gamma solid gas minus gamma solid liquid. You can obtain a solution for this. Okay. You can obtain a solution for this equation. Okay. You can write LT equal to H gamma cos theta divided by 3 eta into T square root, which you can also write it as h into t divided by tau advance into square root. So, here you see that the advancement takes place as square root of t. So, in case of a horizontal channel, okay, if you have capillary flow, the pumping is going to depend or the LT is going to depend as square root of t. So, for a circular channel, for a circular channel, you can write LT as A into gamma cos theta into T divided by 2 eta square root, which is A into T over T advance. Okay. So, with that let us stop here.